So in this session, we're going to focus on the clustering techniques, which is a kind of unsupervised learning, right? So in the clustering techniques, we're going to see what is clustering, why is it important, and what are the different applications of clustering, and what are the different types of clustering techniques. So this is what is the agenda for today's session. All right. So what is clustering, right? And what are the different challenges, applications, different types of clustering techniques? This is what we're going to discuss. So what is clustering? So clustering is a process of grouping a set of objects into multiple groups. Okay. So we have given a data with each data point described as a feature vector. We don't know what is the corresponding target variable. So here we are trying to find out, are there any groups among the data, so that we can use this grouping information for various other applications. Okay, so the clustering is the process of grouping a set of data objects into multiple groups. We also call them as a clusters, so that objects in the one cluster are highly similar to one another, and objects from the different clusters are dissimilar to one another. So we have to make this grouping in such a way that objects belong to the one cluster are highly similar to one another, and objects from the different clusters are dissimilar to one another. So here you see this, it is making a groups in such a way that distance between the points of the same cluster are minimized. Distances between the clusters distances between the instances of the same cluster are minimized, and distances between the points of the different clusters is maximized. Okay, it means we want to form clusters in such a way that intra-cluster distances are minimized and inter-cluster distances are maximized. Intra-cluster distance means distance between the points of the same cluster. Inter-cluster distance means distance between the points of the two different clusters, right? So you want to make this grouping in such a way that intra-cluster distances are minimized and inter-cluster distances are maximized. All right. So this is what is a clustering. Clustering is a kind of grouping so that objects belong to the one cluster are similar to one another, and objects from the different cluster are dissimilar to one another. So here you see this, there are three natural group of data points here. It means we can make three clusters. But the notion of the cluster can be sometimes ambiguous. Suppose if I ask a question, how many clusters are there in this data set? What is your answer? How many clusters in this data set? How many clusters you can see?
It depends on your problem.
No, I'm asking about this particular problem. That what you can see in this slide.
2.
2, 6.
Say 2, somebody said 2, somebody said 6, somebody may say 4, right? So the notion of the clustering may be ambiguous sometimes. Somebody may say 2, somebody may 6, somebody may say 4. All right. So this notion of the clustering can be ambiguous sometimes. But there should be some way of measuring this, what is a good cluster, right? So the good cluster is the one in which this inter-class similarity should be maximized and intra-class similarity should be minimized. And in other words, inter-class distance should be maximized and intra-class distances must be minimized. All right. So a good cluster method will produce high quality clusters with high intra-class similarity. Intra-class similarity means points belonging to the same cluster must be highly similar to one another, or in other words, less intra-class distance. So less intra-class distance is equivalent to high intra-class similarity, because the distance is inversely proportional to the similarity. Similarly, here low inter-class similarity, it means the distance, the similarity between the points of the two different clusters must be dissimilar to one another. It means high inter-class distance. Inter-class distance. All right. So the quality of the clustering results depending on both the similarity measure that we use and its implementation as well. All right. So there are lots of applications of clustering, including in business intelligence, image pattern recognition, web search, biology, security, and many more. All right. Like for example, in business intelligence, we can organize the customers into groups and develop a business strategy for the enhanced customer relationship management. Similarly, in the image pattern recognition, we can use it for handwritten digit recognition, or it can be used for image color compression, and there are many other applications of application even in the image pattern recognition as well. All right. Similarly, in the web search, it can be used to organize the search results into groups and present them in the concise and easily accessible way. Like this, there are various other applications of this clustering is there. So what are the requirements of the clustering algorithm? Suppose if you want to propose some clustering algorithm, clustering technique, what should be the requirement of that clustering algorithm? So one requirement is that scalability. It means we should be able to cluster a big data as well, right? So most of the algorithms works very well on the small data sets, right? But the moment it comes to this big data sets, they may not be scalable to the bigger data sets, right? So the algorithm must be scalable to the bigger data sets as well, and the ability to deal with the different types of attributes. Most of the data sets work for the numerical attribute, but not for the other kinds of data. In general, we have different kinds of data, right? We have categorical data, we have nominal data, ordinal data. Like that, we have different types of data we have in the real world, right? So our algorithm must be able to deal with different types of the attributes. And discovery of the clusters with an arbitrary shape. Most of the algorithms, they can identify the clusters of the spherical shape, but the moment it comes to the clusters of some arbitrary shape, they fail, right? So our algorithm must be able to deal with the arbitrary data shapes as well. And minimal requirements for the domain knowledge to determine the input parameters. So each and every algorithm takes some parameters as the input, right? So while passing these parameters, the user must have the minimal requirement of the domain knowledge. It means without having any idea about the domain as well, you should be able to pass the appropriate parameters for the clustering algorithm. Able to deal with noisy and outlier points, and it should be insensitive to the order of the input records. It should be able to deal with high dimensional data. So again, most of the algorithms may work very well when you give 2-dimensional, 3-dimensional, or some less than 10 dimension. But the moment you have so many dimensions like 100,000 dimensions, then they will fail, right? So our clustering algorithm should be able to deal with high dimensional data as well. And it should be able to incorporate the user specified constraints. And it should be able to interpret the results and improve the usability of these results. All right. So these are the various requirements need to be satisfied by the clustering algorithm. Majority of the clustering algorithms are divided into 4 types: partition based clustering algorithm, hierarchical based clustering algorithm, density based clustering algorithm, and grid based clustering algorithm. So we're going to discuss one each in the partition based, hierarchical, and density based clustering algorithms. So we'll see the brief idea behind each one of this type, and then we'll proceed saying that one particular example in each of these algorithms. So let us start with the partition based clustering algorithm. So it constructs the various partitions and then evaluate them based on some criterion, and then it rearranges them such that it optimizes that criterion. Whereas in the case of hierarchical based clustering algorithm, that it creates some hierarchical decomposition of set of data using some criteria. So you see that there are in some situations like we may want to partition our data into groups at different levels, such as in case of hierarchy. Okay, so hierarchical clustering method works by grouping data objects into a hierarchy or a tree of clusters. Okay, so how to form this tree of clusters or a hierarchy of clusters, we're going to see as we proceed. The next one is the density based clustering algorithm. Okay, so it sees the cluster as the densely connected region, densely connected set of points, right? So it identifies this densely connected set of points as one cluster. So this is very much helpful to identify the clusters of arbitrary shape. All right. So the next one is the grid-based clustering algorithm, in which the algorithm partitions the data space into finite number of cells. We call them as a grid. It's a grid-like structure. Once you form them like a cells, and now the algorithm is not depending on the number of data points. It is only depending on the number of cells. So it only see the cluster as the densely connected cells, not the points. All right. So it forms these clusters based on the densely connected cells. Okay, and the clusters corresponding to the regions that are more dense in the data points than their surroundings. All right. So fine. So let us start with one of the partition based clustering algorithm. One of the partition based clustering algorithm. So far we have discussed what is clustering and what are the challenges in the clustering and why do we need this clustering and what are the different applications of clustering and what are the different types of clustering algorithms. So in which we started exploring one of the type, which is the partition based clustering algorithm. So I hope you are with me so far. Is it clear?
Yes, sir.
Yes. So in the partition based clustering algorithm, we construct k clusters from the given n objects. All right. And each of this partition or each of this cluster is evaluated based on some criterion, right? So based on some criterion, and then we try to swap the point so that this criterion is optimized. All right. So initially we start with some kind of clustering, k clusters. We make the n data points into k clusters, and then we evaluate them based on some criterion, and then we try to swap the points to see that whether this criterion function can be optimized. And then we try to achieve this optimality in the clustering by swapping these points. All right. So here the criterion that we want to optimize is that the distance from the centroid to the individual points in the cluster must be minimized. Okay. So this is what is the criterion. Distance between the centroid and all the points belong to that cluster must be minimized. That is what is the criterion that we want to optimize in this case. All right. So we'll see the k-means clustering algorithm, which is a kind of partition-based clustering approach. Partition-based clustering approach. So this is the process, right? So the input for this k-means algorithm is data set and the k value, where k is the number of clusters that we want to form. That should be given as the input for this k-means clustering algorithm. So we start with initial seed points or initial centroids that we assign them randomly. All right. And then we assign each object to the cluster of the nearest seed point. And how do we judge this nearest seed point? We measure the distance with a specific distance metric. All right. And then we compute the new seed points as the centroids of the clusters. All right. And then we repeat the process until there is no new assignment in the clusters. So we'll come back to this process later, but first go through the example, then you will understand it better. Then again, we'll go through these steps one more time. So this is the example of k-means clustering algorithm. Here we have four instances. So this data set is about the medicine. There are four medicine, A, B, C, D. Each medicine is described on two attributes, weight and the pH index. All right. And the task is to make this four medicine into two groups. Four medicine into two groups, two clusters, basically. Now, the first thing is that we have to assign the seed points randomly. Seed points means the representative points of the cluster or the centroids of the cluster. There are multiple ways of doing. Randomly, you can pick two of the instances and declare them as the centroids or the representative points or the seed points, or randomly assign each object to one of the cluster and compute the average of that cluster. You will get the centroid. Okay, so in this example, we are randomly picking two of the points and declaring them as the seed points of the cluster 1 and cluster 2. So let's say when I randomly choose, A and B are the random points that we have chosen, indicated with the stars. The stars indicating the seed points, initial seed points. So now once you get the seed point, compute the distance from each and every data point to the seed point. Let's say this is seed point 1, which is representing the centroid 1 or the cluster 1 centroid. This is the seed point 2, which is representing the cluster 2 centroid. So now we have to compute the distance between each and every data point present in the data set, and each of these centroids are the representative points. And the distance matrix here is of size 2 by 4 because there are two clusters and 4 data points. All right. So this is A, B, C, D. So this is a distance matrix, and we have computed the distance between each and every point to these seed points. So to compute the distance, we have used the Euclidean distance. Like for example, if I want to compute the distance between D and seed point 1 and seed point 2. So what is seed point 1? Seed point 1 is nothing but this point A. So point A is at 1, 1, right? So now you want to measure the distance between this D. D is what? 5, 4. Distance between 5, 4 and 1, 1. So using the Euclidean distance, we take 5 minus 1 whole square plus 4 minus 1 whole square and the square root of this. Alright, this is how we compute the distance between the point and the centroid. So this is the distance that I have computed and I've got 5. So this is the distance between D and the seed point 1. And this is the distance between D and the seed point 2. And similarly, you can compute it for the other data points as well. Alright, now once you compute this distance matrix, assign each object to the nearest cluster or seed point of the nearest cluster. So please tell me here, look at this A. The distance between A and C1 is 0. Distance between A and C2 is 1. So A is more closer to C1 or C2? A is more closer to C. It is more
C1,
closer to C1, right? So we assign this A to the C1. So cluster 1. So we are assigning a data point to the nearest seed point cluster. So here A is more closer to seed point 1. That is why I am assigning it to cluster 1. Similarly, can you tell me to which cluster should I assign B?
C2.
C2. And to which cluster should I assign C?
C,
C?
C2.
C2. D?
D.
This distance is lesser, right? Which means
Yes, lesser than.
right. So it means we assign to cluster 2. So everybody following it or not? Everybody?
Yes, sir.
Yes.
Yes.
Alright. So now we compute the updated seed points or the centroids. How do we compute the centroid of a cluster? We take the average of the individual data points or the mean of the individual data points, that is the centroid. So as there is only one data point in the cluster 1, that is the centroid. There is no change in it. Alright. So then the cluster 1, we have only one data point, and that is also the centroid. In the cluster 2, we have three data points. Take the average on the x-axis as well as the y-axis. This is the new seed point indicated with a star here. This is the C2 and this is C1. Now again compute the distance between each and every data point to this seed points, updated seed points. And this is the distance matrix that we got here at iteration 1. So this is C1, C2, A, B, C, D. Look at the distance matrix and tell me that to which cluster should I assign this A, and to which cluster should I assign B, C, D, and so forth. To which cluster should I assign A? To which cluster it is more closer?
C1.
C1. So it should be assigned to C1. And what about B?
Again C1.
Again C1. What about the C?
C2.
C2. D?
C2.
C2. Is there any change in the cluster assignment as compared to
Yes.
the previous iteration? There is some
Yes.
change, right? So earlier, all A, B, C, D belong to C2, only A belong to C1. Now it is changed, A and B belong to C1 and C and D belong to C2. Now update the centroid. Centroid is the mean of the individual data point. So we are taking centroid 1, centroid 2. So with rest, these are the centroids indicated in the figure. These two one cluster for now, and these two another cluster for now, and these are the centroid of this cluster. All right. So now compute again the distance from the new centroids to the individual data points, and this is the distance matrix that we got here. This is C1, C2, and this is A, B, C, D. Look at the distance matrix and suggest to which cluster this A, B, C, D should belong to.
C1 A, B, C. No, A, B only. C2, C, D.
Is there any change in the cluster assignment?
No,
There is
sir.
no change in the cluster assignment. There is no new assignment membership. So stop the algorithm and declare the clusters. All right. So this is what is the process. All right. So you can see that algorithm again. Assign each cluster to the cluster of the nearest seed point measured with a specific distance matrix. So compute the new seed points as the centroid of that cluster. All right. And then repeat the process until there is no more new assignments. Okay. So that's what we have done here, right? 3-step process. All right. So
Yes.
declare the clusters. So this is the algorithm. Have you followed it? K-means clustering algorithm. Very simple. Understood?
Yes.
Okay. So let us try to understand what are the strengths of this K-means clustering algorithm and also what are the drawbacks of this K-means clustering algorithm. So strengths are that it is very easy to understand and implement, and it is efficient also in terms of its time complexity. The time complexity of the algorithm is order of TKN, where n is the number of data points, k is the number of clusters, and t is the number of iterations. All right. So it is very efficient in terms of the time complexity as well. Weakness of this include many. Okay, so let us try to understand each one of them one by one. So the algorithm is only applicable if the mean is defined. Suppose if the mean is not defined, then it doesn't make any sense to apply this algorithm. And user needs to specify this k explicitly, and for that he may need some domain knowledge. And the algorithm is sensitive to the outlier points. So what are the outlier points? Outlier points are the data points that are very far away from the other data points. Okay. So these outliers could be errors in the data recording or some special data points with very different values. Okay. So how to handle this weakness? Okay, you see this. This is the problem with the outliers. There is a one outlier point which is very different from the other data points. Suppose if you ignore this data point and form the clusters, then you may end up with the optimal clusters as you see here. Instead, if you try hard to incorporate this outlier point into the model, into the clustering process, then it may lead to the undesirable clusters as you see in the first figure, right? So to address this, we have different ways of addressing this. So one method is remove some data points in the clustering process that are much farther away from the from the centroids than the other data points. So suppose while making the clustering, if you observe the two strange points, it means the distance is too much, then keep track of it for a few number of iterations, and then after few number of iterations also it is still the same, then you can remove those points in the clustering process itself. Or another method is perform some random sampling. It means randomly pick up the sample and apply the clustering technique, and then remaining points assign based on this to which cluster these are, to which cluster centroid these new points are closer. All right. Because you're picking a random sample, the chance of getting an outlier point into this random sample is very less. right? That way also you can avoid this outlier points. Okay, so the another disadvantage of this k-means clustering algorithm is that it is sensitive to the initial seed points that we select. Suppose initially when you initialize the seed point, let us say there is a one seed point here, one seed point here, one seed point here. You see that all these instances are close to this and seed point, and all these data points are close to that seed point. And whatever you do, this will be the same. It means there will be no change. Therefore, the algorithm will stop and then it will declare the clusters like this. Whereas the optimal clusters are this, right? So it means it is sensitive to the initial seed points that you are picking. There are many algorithms that how to pick up a right seed point so that the algorithm will converge fastly, as well as you will get the desirable clusters. All right. Another weakness of k-means clustering algorithm is that it cannot identify clusters of arbitrary shape. So if you see this data set, there are two clusters. One cluster is this and another cluster is this. They are of arbitrary shape. So it cannot identify the clusters of arbitrary shape and forming a spherical clusters, as you see in the right side figure, right? So these are the disadvantages with the k-means clustering algorithm. What are the disadvantages? Disadvantages are it is sensitive to the outliers, it is sensitive to the
K
uh,
value.
k value, initial seed points, initial seed
Yes,
points.
exactly.
You have to explicitly specify the k value, and it cannot identify the clusters of arbitrary shape. So these are all the problems with this k-means clustering algorithm. Have you followed the k-means clustering algorithm completely?
Yes, sir.
Okay. So the
So,
next one, yes.
so you said that we will be also seeing what are the techniques which we use to identify the seed point because it is sensitive to.
No, we'll not be seeing that in this, but there are
That's
algorithms
yes.
like power k means that which is handling this how to, and there are some explicit methods also to
Okay.
intelligently specify the seed points so that it will result in the optimal clustering.
Okay.
Yeah. The next one is the hierarchical clustering approach. So the hierarchical clustering approach is like identifying the uh, uh, hierarchy of the clusters. So, in some situations, we may want to partition our data into groups at different levels or different hierarchies, like a tree-like fashion. Like you see that, suppose if you want to group, suppose you went to library, then you may see the two different kinds of groups, journals at one place, then books at one place. Suppose if you go to the book side and all the CSE books are at one place, all the EEE books are at one place, all the CC books are at one place, and so on. So this is another level of hierarchy, another level of clustering at the different hierarchy or at a different level. Suppose now you go to the CSE books. All the artificial intelligence books are at one place, all the operating system books are at one place, all the algorithm books are at one place, and so on. Right, this is a different level of hierarchy and different clustering. Now, suppose if you go to the AI books again, that you may have found out all some other books are placed at one place, different other books are arranged. I mean, basically you are grouping them at different levels of hierarchy. All right. Suppose if you have any such applications, then hierarchical clustering is useful. So the hierarchical clustering, it can be either agglomerative or it can be divisive. So agglomerative is a bottom-up approach in a sense that we start with each one data point as a one cluster and we gradually uh, combine them into larger and larger clusters. Okay, and divisive approach is a top-down approach. Initially, we start with all objects as a single cluster. Then we subdivide them into smaller and smaller clusters. Okay, so we'll see that with a graphical presentation here. So this is the agglomerative approach. Initially, we take each data point as a one cluster, and we always try to merge the two closest clusters. Let's say A and B are the closest clusters. We're merging. Now we have 4 clusters. AB one cluster, C another cluster, D, E are 2 more clusters. So now we again merge the 2 closest clusters. Let us the D and E are the 2 closest clusters. Again merge the 2 closest clusters. Repeat the process until you get a single cluster. Alright. So depending on the requirement, you can cut this. We call this as a dendrogram, which is indicating the sequence in which we merge these clusters. All right. So you can cut this dendrogram at the appropriate level to get the clusters. All right. So this is the agglomerative approach. Divisive approach is reverse of this. It means we start with all the elements as a single cluster. Then we divide them into smaller and smaller clusters so that objects from the same cluster are similar to one another and objects from the 2 different clusters are dissimilar to one another. So like this, we divide till you get only one object in each cluster. This is the divisive approach. Okay. So here is the dendrogram. This is a binary tree-like structure that shows how the clusters are merged or split hierarchically. So each node in the tree is a cluster. Each leaf node is a singleton cluster. Suppose if I cut the dendrogram at this level. So how many clusters do I get if I cut the dendrogram at this level? All this branch is one cluster.
7.
This branch is another
Okay.
cluster. So
Like
how many clusters were we getting? 2 clusters.
2.
So how many clusters do I get if I cut the dendrogram at this level? This is one cluster. This is another cluster.
3.
3 clusters, right? So clusters of the data object is obtained by cutting the dendrogram at the desired level. So each connected component forms a cluster. Suppose if I cut the dendrogram at this level, then these connected components, 2 connected components forms 2 clusters. Suppose if I cut the dendrogram at this level, we have 3 connected components and we get 3 clusters here. All right. So like this, we can get the clusters based on based on the requirement. So now the question is, how do we merge the clusters? So we are saying we are merging the 2 closest clusters. 2 closest clusters. It means we are finding or determining the distance between the clusters. So how do we determine the distance between the clusters? We know how to measure the distance between the points, but how to measure the distance between the clusters? Because the cluster is not just a single point, it is some set of points. So how do we measure the distance between the clusters? There are different ways of doing it. Depending on the distance metric that we use, we have different agglomerative techniques like single link, complete link, average link, and centroid distance based. All right. So here distance between the clusters are defined as the distance between the points in them. All right. So suppose if we use the closest distance as the distance between the clusters, it means you find out the distance between all the pairs of points from the 2 different clusters and pick up the minimum distance. Then we call that as a single link agglomerative clustering. So if I use a smallest distance possible between the clusters as the distance between the clusters, then we call that as a single link agglomerative clustering. Suppose if we use the farthest distance as the distance between the clusters, max farthest distance as the distance between the clusters, then we call that as a complete link agglomerative clustering. Suppose if we use the average distance, then we call that as the average link agglomerative clustering. It means find out the distance between all the pairs possible between the clusters and take the average of all these distances. Then we call that as the average link agglomerative clustering. Suppose if I find out the centroid of each one of this cluster and distance between them, if I consider as the distance between these clusters, then we call that as a centroid distance based agglomerative clustering. So 4 things: single link,
This
complete link,
medium is
average link.
represented the distance between the means of the clusters. Means. Shit.
Madam, any query? Geeta madam. Centroid distance based.
Yes,
Any?
centroid once.
Centroid. Okay, find out the centroid of the individual cluster, and then distance between the centroids is the distance between the clusters. That is the centroid distance based agglomerative clustering. Clear, madam? Find out the centroid. This is the centroid is one data point, right? I mean, d-dimensional vector. So this is also d-dimensional vector. Apply Euclidean distance between them. You will get the distance between the clusters. Clear? All the 4: single link, complete link, average link. I mean, idea is clear. We'll see the example. Don't worry about that. But is the idea clear? Different options to find out the distance between the clusters. So what the single link is doing?
It is calculating the distance between all the points, but the minimum one it is picking up.
Minimum one is the distance between the clusters. Okay, minimum distance is the distance between the clusters. What about the complete link?
It is picking first calculating all the distances, then picking up the maximum one.
Farthest distance, maximum. Average link is average of all the distances. Centroid one is, it is first computing the centroid of the individual clusters, and distance between the clusters is taken as the distance between the centroids is taken as the distance between the clusters. All right. So we'll see an example. So here is an example of one-dimensional data. There are 5 data points A, B, C, D, E. Each one of them is described on a one-dimensional space. And let's say that cluster 1 is having A and B. Cluster 2 is having 3 points C, D, E. So now I ask you to find out the distance between cluster 1 and cluster 2. Distance between cluster 1 and cluster 2. What is the distance using the single link? What is the distance using the complete link? And what is the distance using the average link? And what is the distance using this centroid base? Tell me. A and B belong to one cluster. C, D, E belong to another cluster. What is the smallest distance possible between these two clusters?
So distances are calculated using Euclidean only, no?
Euclidean only. But for one-dimensional data, Euclidean is equivalent to the absolute value.
So directly subtractions to be done, sir.
Subtraction.
In A and C,
2
1
is the
4.
minimum.
2 is the minimum, right? See that between B and C. Am I right? Right. So the minimum distance is 2. It means the distance between C1 and C2 is 2 according to this single link. Okay. So madam, what is the Euclidean distance? Euclidean distance is square root of x1 minus x 2 data points, x1 and x2 I say. So x11 minus x12 whole square plus x12 minus x22 whole square plus on x1d minus x2d whole square. If d equal to 1, this is just this, right? It means the square root of x1 square minus x1 minus x2 whole square. So which is equivalent to the absolute value of x1 minus x2, isn't it? Square and this get cancelled. Hello,
Yes,
madam.
yes.
Yes. Yes. What is the farthest distance possible between these two clusters?
5.
5, which is in between 1 and 6, right? Right. So that is 5 according to the complete link. What is the average distance? What are the pairs, by the way? Pairs of
A,
AC,
AC, E, BC, ED, BE.
BD. Okay, compute all the distances and then take the average, which is 3.5. Can you tell me what is the average? I mean, centroid distance between centroid based distance. Okay, a centroid distance.
Mean of
Mean, what is the mean of this cluster?
1.5.
And what is the mean of this cluster?
10,
5, right?
5.
So what is the distance between them?
3.
1. So this is the centroid distance based agglomerative cluster. Alright. So we'll see the process. Then we will see one of this agglomerative clustering with an example. The process is very simple. We initially start with each one of the object as one cluster, and then we compute the distance matrix, and then we pick up the two closest clusters and merge them. This process is repeated until we have only one cluster. Okay, very simple. So we'll use a single link agglomerative clustering. We take an example and solve it using the single link agglomerative clustering. So here is an example of 6 data points A, B, C, D, E. Each data point is described on 2 dimensions, x1 and x2, as you see here. This is the data matrix. All right. So now each one is one cluster. Each one is one cluster. Because each one is a one cluster, there are 6 clusters. So now suppose if I ask you to find out the distance between the clusters, all pairs of clusters, what will be the size of the distance matrix? 6 by 6, as there are 6 clusters. 6 by 6, and this is the distance matrix. And we use the Euclidean distance here to compute the distance. As there is only a singleton point each one of them, distance between the clusters is equivalent to distance between the points, as there are only one point in each cluster. So this is the distance matrix. Look at the distance matrix carefully and tell me what is the minimum distance among all the entries, and between what?
0.50 between D and F.
0.50 between D and F. It means D and F are the
And
two
one more,
closest clusters.
acha, there also 0.50.
This is a symmetric, madam, because it's a symmetric, lower
Yeah.
half equal to
Same.
upper half. So it is between D and F only. Please notice that. There also it is between D and F only. This or this, both of them are same, between D and F. Okay. So between D and F, so it means D and F are the two closest clusters. It means merge them together, right? So now if you merge them together, how many clusters you have now? You have 5 clusters. What are the 5 clusters? A is one cluster, B is one cluster, C is one cluster, D and F one cluster, and E is another cluster. Total 5 clusters. Now what will be the size of the distance matrix now? 5 by 5. Okay. So this is 5 by 5, but do we have to update all the entries or very few entries with respect to the new cluster?
With respect to the new cluster,
New
we have
cluster, if I update it, it's done, right? Rest of the things will not change. The distance between A and B will not change, A and C will not change. Only with respect to the new cluster, I have to identify or I have to compute these distances. So this is the new cluster DEF. So this row and this column, which is a symmetric anyhow. It means distances from other clusters to this new cluster must be computed, right? So now let us say if I want to compute distance between cluster A and cluster D and F using single link agglomerative clustering, what should I do? I compute the distance between A and D. I compute the distance between A and F. So whichever is minimum, I pick up that as the distance between these two clusters. Am I right? Using single link.
Yes, sir.
Right. So that's what it is doing here. So compute the distance between DA and FA, pick up the minimum, right? Which is the distance between this cluster DF and A, which is 3.20, which is here, DF and A, DF and A. Similarly, for other things also you compute, fill up this row and this column. Now look at the distance matrix carefully and tell me that what is the minimum value that you can see in the distance matrix between what?
A and B.
A and B, which is 0.71, right? So it means the closest two clusters are A and B. Merge them together. A and B. Now we have 4 clusters, AB one cluster, DF another cluster, C one more cluster, and E another cluster. Now the distance matrix size would be 4 by 4. Now we have to fill up these distances with respect to this new cluster. Update the distance matrix again using this single link distance measures, right? So this is the new cluster, new distance matrix. So which is the minimum distance? 1, and between E and DF, right? So merge this E and DF together. So now we have 3 clusters, AB one cluster, ADF another cluster, C is another cluster. And this is the distance matrix, updated distance matrix. Again, look for the 2 closest clusters. This is the 2 closest clusters, C and DEF. Merge them together, right? So after merging them, we have 2 clusters, and you can merge them together and form a single cluster. So now if you express this, the sequence in which we have merged these clusters using a dendrogram, it looks something like this. So first D and F are merged, then A and B are merged, then E and DF are merged, then C and EDF are merged, then AB and CDEF are merged, right? So this is the dendrogram. Once you can cut the dendrogram at the appropriate level and form the desirable clusters. All right, fine. So is the process clear? Is the process
Yes.
clear? Yes.
Yes.
So now the question is, which distance measure is better? The single link or complete link or average link or the centroid dist? Okay. So we can't say one particular distance measure is better. So each method has both advantages and disadvantages, and it basically depends on the application. There are single link, complete link are the most commonly used. If you take the single link agglomerative clustering, advantage with this is that it can find clusters of arbitrary shape also. All right, but the problem with this is it is sensitive to the outlier points because of the chaining effect. Even one point is closer, it will form that as a part of the cluster, right? That's the problem with this single link. If you take the complete link, average link, or the centroid distance based, they are more robust to the outliers as compared to the single link. But the problem with this is that they may tend to break the larger clusters into smaller clusters, and they cannot identify the clusters of arbitrary shape. So they prefer the spherical shape clusters. All right. So these are the problems with this hierarchical clustering approaches. All right. So although it is solving some of the problems of the K-means clustering algorithm, it is still not robust to the outlier points, all of them. And one more important problem that we have here is that they cannot identify the clusters of arbitrary shape.
Shape,
Alright?
yes. So,
Yeah.
sir,
So
these kind of things can be picked up as their research work to work in this.
clustering, yeah, although some research is going, mostly it is exhausted, madam. Uh, um, but then people are still working as part of some applications. Okay, as an application they are using.
Yes.
Yeah, for in solving some problems, if some grouping is required as part of that algorithm, then they are taking this and applying there. But yeah, as I have told that,
Algorithm level research is exhausted.
yeah, no, it's not. You can't say it is exhausted because I could see some papers that people are publishing, although it is, I mean, not very high in number. People are still publishing at very good conferences also. Like recently, I think in 2020, that somebody published Power K-means. That is not sensitive to the initial seed points or something like that they have proposed. I haven't read the paper completely, but yeah, so it means in A-star conferences also people publishing. But only thing is that you have to really spend the time to identify what is the problem with the existing methods and how can you approach it. Right? It's not that something you get very easily with a quick modifications, because so many people already work and there are a lot of variations and thousands of algorithms are already there. So to come up with something very new idea, you need to have an idea about all these existing techniques. Okay, so
Yes.
that may be slightly difficult for somebody who is starting it right now. Okay, that's what I
Yes.
mean to say, that it is exhaustive. But still, some active research is going on in the clustering, the core part of the clustering also. All right.
Okay.
Yes. All right. So we have DB scan algorithm, which is based on the density based clustering method. This density based clustering algorithms, they see the cluster as the densely connected region of the data points. Okay. So like for example, you see that these are the densely connected points. This is another densely connected region. This is another densely connected region. This is another densely connected region. You see that this is another densely connected region. This is another densely connected region. All right. It means clusters are the dense regions in the data space separated by the regions of the lower object density. All right. So it means cluster is defined as the maximal set of densely connected points. All right. So the advantage of this is that they can discover the clusters of arbitrary shape, and they handle these noisy points or outlier points automatically, and you need not specify the number of clusters explicitly. It will automatically identify the clusters also, and more importantly, it scans the database only one time. You see this K-means clustering algorithm, it is scanning the database for multiple times. At each iteration, at one time it is scanned. So the number of scans is equivalent to the number of iterations that the algorithm is proceeding, right? But here, DBScan algorithm, it scans the database only one time. This is the important property for somebody who is measuring this time complexity, because every time when you scan the database, complexity of this algorithm will increases, because the database will be in the secondary disk. You have to load that into the primary disk, and all this is a time taking process. All right. So this is one more important property of the density based clustering method. Okay. So before we're gonna see the algorithm, we need to understand certain notations. All right, certain what is that key concepts that are required to understand the algorithm. So here, although it doesn't take the number of clusters as the input, it does take some of the parameters. So the inputs for this algorithm is epsilon and the minimum points. Epsilon is the maximum radius of the neighborhood. So if we say that here, like for example, this is the epsilon neighborhood of this data point, and this is the epsilon neighborhood of this data point, and this is the epsilon neighborhood of this data point. It means starting with this point as the center, if you draw a circle, right, or I mean any other in the higher dimensional space also, you can visualize it like a sphere or whatever. Okay, so with that radius, right, what is the neighborhood, right? Maximum radius of the neighborhood, that is measured with this epsilon. Minimum points is the minimum number of points within the epsilon neighborhood of that point. Okay, so these two are the parameters of this model. All right, so I'm just defining the notations and the key concept required to define an algorithm, discuss an algorithm. Okay, so we'll be discussing three kinds of points. One is the core point, the other one is the border point, the other one is the noisy point. We say that a point is a core point if it has more than minimum number of points within the epsilon neighborhood. Like for example, you see this is a core point because within its epsilon neighborhood, there are more than 4 points, where 4 is the minimum number of points specified, which is the kind of parameter that we are specifying. If minimum number of points are 4, within the epsilon neighborhood of this, there are more than 4 number of points, therefore it is a core point. Okay. Border point is not a core point, but it is within the border of another core point, right? Within the epsilon neighborhood of another core point. Border point is not a core point, but it is within the epsilon neighborhood of another core point. You see that within its epsilon neighborhood, we don't have more than 4 points, but this point is within the epsilon neighborhood of another core point. That is why we call it as a border point. If the point is neither a core point nor a border point, we call that as a noisy point. Okay, so example is this. This is within this epsilon neighborhood, we don't have minimum number of points, therefore it's not a core point. And this is not within the epsilon neighborhood of any other core point, therefore it is not a border point also, therefore it is a noisy point. Okay, so understood the difference between the core point, border point and the noisy point? Understood the difference? Core point, border point, noisy point. Should I repeat?
Yes, sir. No, no, sir. Clear.
Clear. Okay, fine.
Anybody else?
Anybody else who want me to repeat? Is it clear?
Yes, sir.
Repeat,
Noisy
Ramya madam.
point. Yes, sir.
Noisy
Noisy point.
If the point is neither a core point nor a border point, we call that as a noisy point, madam. It means within the points epsilon neighborhood, we don't have minimum number of points. Therefore, it's not a core point. And this point is not within the epsilon neighborhood of any other core point. Therefore, it is not a border point. So if it is neither a core point nor a border point, we call that as a noisy point. This is an example for that.
Oops.
Within this epsilon neighborhood, we don't have minimum number of points. Therefore, it's not a core point. And this is not within the epsilon neighborhood of any other core point. Therefore, it is not a border point too. And therefore, it is a noisy point. Clear, ma'am? Ramya, ma'am?
Yes, sir.
Yeah. Another concept is density reachability. So when do we say that one point is densely reachable from another point? So like for example, here we say that object Q is directly density reachable from P. Okay, so density reachable from P. So if we have to say this, it has to satisfy two properties. One is that P must be a core point and Q must be within the epsilon neighborhood of P. Alright, then we say that Q is density reachable from P. Q is density reachable from P. If we have to say this, P must be core point, okay, and Q must be within the epsilon neighborhood of this P. Then we say that Q is density reachable from P. So you see that here P is a core point because it has got minimum number of points within this epsilon neighborhood, and this Q is within the epsilon neighborhood of P. That's why we said that Q is density reachable from P, directly density reachable from P. Alright. So now can you say that P is density reachable from Q? If it has to happen, what are the
Then
conditions?
Q need to be the
Core point, right? Is the Q
yes.
core point?
No, sir.
It's not a core point, right? It means
Yes.
although Q is density reachable from P, P is not density reachable from Q. So it means density reachability is asymmetric, not symmetric. Okay. So it means if Q is density reachable from P, we cannot imply that P is density reachable from Q. Alright. So the density reachability is asymmetric. And density reachability can be direct or it can be indirect also. So for this in this example, density reachability is direct. If you take this example, density reachability is indirect, right? It means there are chain of density reachabilities from P to Q, Q to P. So you see that Q is directly P is directly density reachable from P2 and P2 is directly density reachable from P1 and P1 is directly density reachable from Q, but P is indirectly density reachable from Q. Alright, so there are chain of density reachabilities through which we can reach P. Alright, and this indirect density reachability also not symmetric. Alright, clear, right? what is direct density reachability and what is indirect density reachability. Clear? Everybody?
Yes.
Yes. The next one is the density connectivity. Density connectivity, we say that P and Q are densely connected to one another. If
So,
they
sir,
are,
so these points are so near, but still so many clusters. And then again,
no, these are not clusters.
yes.
These are not clusters.
Okay.
Don't mistaken. These are not clusters. See, this is the epsilon neighborhood of one of the point. Similarly, this is the epsilon neighborhood of another point.
Okay.
Another point like that. Okay. These are not the clusters. We'll see how to form the clusters. I'm just demonstrating some basic concepts required to understand the algorithm.
Okay.
Okay. So far I have discussed what is epsilon, what is minimum number of points. These two are the parameters of the algorithm. And then I started discussing what is the core point, what is the border point, what is the noisy point. Then I started discussing density reachability. Density reachability is asymmetric and it can be direct density reachability or it can be indirect density reachability. So are these concepts clear so far, whatever we have discussed?
Yes, sir.
Sir,
Yes,
go
sir.
to previous slide, sir. Here you said Q is directly density reachable from P. Why not the other way?
Because if Q has to density reachable from P has to density reachable from Q, then Q must be a core point. But here Q is not a core point, no?
Oh, we say why it
We
is
say
not.
that P is like say you see that P is density reachable from Q if it satisfies two properties. One
Hmm.
property is P must be a core point.
Yes.
Q is density reachable from P if P is a core point. The second one is Q is within the neighborhood of P.
Yes.
I mean,
Yes.
within the epsilon neighborhood of P. Right? If any of this condition violates, then this density reachability is not satisfied. Got
Yes.
it, madam?
This. Yes. The same is applicable for other also.
No, actually here P is a core point, no? Because
Achha.
minimum number of points is 4.
Ha. Yes, sir. Yes, sir. Okay. Okay. Yes.
This is a core point and Q is within the epsilon neighborhood of
Yes.
P.
Yes. Yes, sir. Yes, sir. Okay. Okay. Thank you. Thank you.
Yeah. So density connectivity. We say that P and Q are densely connected to one another if they are commonly density reachable from some other point O. Right, you see that there is a point O from which both P and Q are densely reachable. Therefore, this P and Q are densely connected to one another. And density connectivity is symmetric in the sense that if P is density reachable from Q, Q is also density reachable from P. Alright, so this is the density connectivity. Alright, so it means P is densely connected to Q. It also implies that Q is densely connected to P. Alright, so we are ready to discuss the algorithm now. Okay, but before that, tell me one thing. If there are 2 points, okay, and if P belongs to the cluster 1, and we also said that Q is density reachable from P, then Q must belong to C1 or not? If there are 2 points P and Q, if we say that P is belonging to cluster 1, and we also said that Q is density reachable from P, okay, so Q must belong to C1 or not?
Yes.
Yes, sir.
Yes.
Right, because it is within the dense region of that P only, right? Right. So for all the points P and Q belongs to cluster 1, if P belongs to C and Q is density reachable from P with respect to the epsilon and minimum points, then Q also must belong to C. Okay, so it means for any pair of points P and Q, if P is belonging to the cluster already, so ignore this. Okay, if P is already belonging to the cluster and Q is density reachable from P, then Q also must belong to the same cluster. All right, and if P is densely connected to Q with respect to epsilon and minimum points, then if P is already belonging to cluster, then Q also must belonging to that cluster. It means any two densely connected points or densely reachable points must belonging to the same cluster. That's what the summary of the 2 points. All right. So using this, we form a DB scan algorithm. So this is the DB scan algorithm. Input for this is epsilon and minimum number of points. So for each object P in the data set, if P is a core object and not yet processed, then we retrieve all the objects that are density reachable from P. Make all the objects in the C as processed, right? And report C as a cluster. Else mark P as an outlier point. Okay. So repeat this process until all the objects in the data set are covered. We'll see an example, then it will be more clear to you. Here is an example of epsilon with epsilon equal to 2 and the minimum points is 3. So we start with some random point, explore the neighborhood of that point and explore the neighborhood of those points, explore the neighborhood of those points, repeat this process until there is no neighborhood point covered within that epsilon neighborhood of these points, okay, and make them as one cluster. All right. So once you don't find any other point within the epsilon neighborhood of these points, declare that one cluster and again start with another random point. So let us say I again started with some other random point and let us say this is the point and you don't have any point within the epsilon neighborhood of this point. So therefore you declare this as a noisy point or the outlier points and ignore it. And you again start with another point, explore the epsilon neighborhood of those points and repeat the process until all the objects in the data set are covered, right? So similarly here, you're starting with the red point, exploring the epsilon neighborhood, which is indicated with the sky blue color, and explore the epsilon neighborhood of those points, sky blue color points also, until you don't find any point unexplored within the epsilon neighborhood of any of these points. All right. So you repeat this process and then declare that as a one cluster, and then again start with another random point. All right. So is the algorithm clear? So you're scanning the database only one time. You need not specify the K value explicitly, and it can identify the clusters of arbitrary shape, and it is not sensitive to the initial seed points, and it is not sensitive to the outlier points. Okay, so these are the advantages of the DB scan algorithm. It is not sensitive to the initial seed point that you have chosen. It is not
Yes, sir.
sensitive to the outlier point. It is
Yes.
You need not specify the K value explicitly, number of clusters explicitly, and it scans the database only one time, and it can identify the clusters of arbitrary shape. Okay, so these are
So,
all.
sir, it is, it is able to cover all the weaknesses of K-means.
Yes. But there are some disadvantages of DB scan algorithm also that we're gonna see.
Yes.
Okay. The disadvantages of this DB scan algorithm is that it is hypersensitive to the input parameter setting. Okay, so this densely connectivity is highly depending on epsilon and the minimum points. Okay, so if you vary them, you may get a different kinds of clusters. Okay, so it cannot handle the varying densities. Like for example, here you see that this is, if you see here, there is a one kind of density. If you see here, there is another kind of density. So it cannot handle the varying densities. This is the first disadvantage, and it is sensitive to the input parameter setting also. With the different input parameters, you may get different kinds of clusters as you see in this figure. All right. So these are the disadvantages of the DB scan algorithm. Advantages are it can have arbitrary shaped clusters, right? Number of clusters is determined automatically. You can separate the clusters from the surrounding noise. Disadvantages are input parameters may be difficult to determine, and in some situations it is very sensitive to the input parameter set. That's
So,
all. Madam, tell me. Madam.
64th slide.
Yeah, coming.
So, you just gone little fast, sir. This slide,
You want me to explain this?
this slide here.
Yeah. See, madam, this algorithm is sensitive to the input parameter setting. Like, for example, if I choose some epsilon, it may just make it as a one cluster, as you see here. If I choose some very smaller epsilon and the minimum number of points also very smaller, then it may form a clusters like very many number of clusters, as you see here. It means with a different number of input parameter, with a different input parameter setting, we get different clusters. It means there is a tendency of breaking larger clusters into very small clusters, one cluster into many small clusters, or it has a tendency of combining multiple clusters into one cluster depending on the input parameter setting, madam. Yeah, that is the disadvantage of the DB-scan algorithm, and it is slightly difficult to determine the right parameter setting. It's a hyperparameter to tune.
Okay.
One has to try different things and see. Yeah, we'll see that also in the demonstration. Okay.
Sir, we have not covered grid-based, sir.
Grid-based, yes. That is not included as part of this, but the extension is very simple. See, earlier I used to take this for 2 hours actually, because nobody asked the queries. It went so fast and completed within 1 hour 20 minutes. That's why I didn't include. That time it was taking a lot of time and it was not possible to cover within 2 hours. That's why I didn't include. Yeah, but you can explore. That is also simple. Initially, we make the grid-like structure, and based on the count of the number of points within the grid, and we also compare the neighborhood cells, and we combine the cells that are densely connected to one another. And the advantage of this grid-based algorithm is that the algorithm is independent of the number of data points. Once you form the grid-like structure, it is only dependent on the number of cells. That way, it is much faster as compared to the other algorithms, other kind of algorithms that we have discussed. It means they are highly scalable to the big data. These grid-based algorithms, madam. So there, once you form the grid-like structure, no, there is a separate algorithm to form a grid-like structure on the cells. It looks more or less similar to the grid-based algorithms on the cells. Okay, so that way you will easily understand it. But only thing is that you need to just understand the algorithm to form a grid-like structure. Yes, madam, please.
So this over here, you said it depends upon the number of cells. So those number of cells are directly proportional to the clusters, or no?
No, not clusters,
Data.
neither clusters nor the points. Not the
Okay.
points, they're not densely.
It depends on the
like
data.
in one cell you may have 100 data points also. In one cell you may have
Yes,
just
yes.
1-2 data points. It doesn't matter. It actually doesn't depend on the number of data points.
Sorry, yes.
So any other query, madam? Otherwise we'll move on to this hands-on part.
Thanks to the numerical problem after every algorithm, otherwise, understanding algorithm.
Yeah. So we'll be seeing two applications of the clustering. Okay, that is handwritten digit recognition is one of the application, and image color compression is another application that we're gonna see in the hands-on. So before that, let me show you how to apply the clustering algorithm, or how to implement, how to import these clustering algorithms and make use of them to form clusters. Okay. So here are some of the libraries for the visualization purpose I have imported. So here's a sample data set that I am generating. Make blobs. So need not introduce this much because we have already seen this make blobs in the visualization part. So this makes a data set of blobs. something like this, right? So we are making 4 blobs here with the number of data points as 300 with 4 centers. And this is the cluster standard deviation. And this random state I have fixed because it's a demonstration and I want you to get the same data set. All right. So I'm just scattering the same data set. This is the size that I'm giving for the data points. The size is 50 I'm giving. Okay. And this is how the data set looks like. Okay. Where is this? So this is how the data set looks like. How many natural groups are there in this? There are 4 natural groups, right? So now let us try to apply some clustering algorithm on this data set with a number of clusters as a 4, and let us see whether it will be able to recognize these 4 natural groups present in the data set or not. All right. So here I'm using the k-means clustering algorithm. All the clustering algorithms are there in sklearn.cluster. So from sklearn.cluster, I'm importing k-means clustering algorithm, and I'm calling this k-means clustering algorithm by passing the number of clusters equivalent to 4. All right. So directly also you can call with 4. It will take it as a number of clusters only. All right. You can also specify the n underscore clusters equivalent to 4. So now once you get this model, fit it for the data X, okay, and predict it for the same data. So here you see that you're not passing the corresponding target value. You're only using the feature vectors to make a cluster because it is an unsupervised learning. So you're calling model.predict on the same for the same data. So to indicate that to which cluster this it belongs to. So this is the YK means indicating the point or indicating to which cluster each of the data point belonging to. All right. So now I'm scattering the same data set, but this time I'm assigning the color based on the labels that the k-means algorithm is giving. Based on this, I'm assigning colors. It means each and every group is indicated with a different color. So the color is assigned based on the Y k-means value, right? So if the YK means value is 1, I may pick one color. If YK means value is 2, then I pick a different color that for that point. Size is 50 only. Color map this I am selecting here. So, and I am also trying to plot the cluster centroids. So to access the centers, pick up the model dot cluster underscore centers underscore. All right. So once you get the centers, just scatter them based on the centers. Centers colon comma 0, centers colon comma 1. It means each center is a 2-dimensional point as the data itself is a 2-dimensional point. So now I'm indicating that with a black color with a different size as well, bigger size equivalent to 200. I'm also putting some transparency in the color 0.5. All right. So this is how the data looks like now. Okay. So you see that there are 4 clusters, 4 natural groups, and those are the centroids. The big black color points are the centroids. So does it, will it, does it, can it, is it recognizing the 4 natural groups present in the data set or not?
Absolutely.
Absolutely right. It could recognize the 4 natural groups that are present in the data set. So that is the k-means clustering algorithm. Now let us take a different data set where this k-means clustering algorithm fails. All right. So one of the disadvantages that we said is that it cannot identify the clusters of some arbitrary shape, right? So let us see that kind of data. So this time I'm making the make moons data, and data looks something like this. All these purple color points belong to one cluster, yellow color points belong to another cluster. So you see that I'm calling this make moons data, creating 200 points with a noise of 0.05. This defines the spread of the data points. And I'm just scattering them, and the color map I'm assigning based on the Y value, right? So we have the corresponding class label also for this data. So I'm just using that label information for the plotting purpose, not for the clustering purpose. All right. So you see that this is the data set. It means our algorithm should be able to identify these 2 natural groups present in the data set, 2 moons. Each moon is one cluster, right? So let us apply k-means clustering algorithm. This time I'm calling directly and calling fit predict also directly. So I'm not taking a model, then fit, then predict. So this is a 3-step process. You can do it in a single step also. K-means clustering algorithm with number of clusters equal to 2 and calling fit underscore predict. So because you're fitting and predicting for the same data, you can directly call fit underscore predict, which will fit the data and predict it. So you got the label here. Now I am plotting this same data points, and this time I am assigning these colors based on the predicted labels. All right. So this is what is the clusters that it is identifying. So you see that it cannot identify this natural group of clusters that are present because they are of arbitrary shape. So it is still making some spherical shape clusters, but that assignment is not correct, isn't it? These are not the correct cluster assignment, right? But the k-means algorithm making this kind of clusters. It means it is failing to identify the clusters of arbitrary shape. Agree?
Yes, sir.
Right. So now I'm importing dbscan this time. Right. So dbscan algorithm with epsilon of 0.3 and minimum number of samples equal to 5. And I'm calling fit underscore predict of this x, and these are the labels. So now I scatter them based on the color map equivalent
So
to
without
this.
training, sir.
Training. This is training. The fitting and predicting both are done at a time.
Okay. Yeah.
Yeah. So yes, because this time the color maps are based on the labels one, which is the labels given by the prediction given by the dbscan algorithm. So now you see that it can, okay, okay. I think I didn't execute the previous one. You see that now it can identify the clusters of arbitrary shape, right? But as I have mentioned to you, it is very sensitive to the input parameter setting. Suppose if I give some 20 here, let's say. Now you see that it is breaking these larger clusters into smaller clusters, right? Right.
Really.
Yeah. And suppose if I increase this, let's say 0.5, and I give, let's say, some 10 here. I don't know what it will get. Yeah, you see that it is making it into some single cluster only, right? Everything. So it is very sensitive to the input parameter setting. Okay. So now you might have realized that what I meant by that slide.
Yes.
Yes. Okay. So now we'll see the two applications of this clustering. That is digit recognition problem, as well as this image color compression. So image color compression is one of my favorite application of the clustering. Okay. I hope that will become a favorite for you too. So let us.
Sir, image processing is your research area.
No, madam. My research area is recommender systems. All right. We have worked on some other problems also, like multi-label classification, multi-class classification, matrix sector. We have worked on other things also, but not on the image process. Okay. All right. So k-means clustering algorithm on the digits. All right. So digits means how many clusters?
10.
10, right? As there are 10 digits, right? So I'm taking the real-time data set for this. So let me open and whiteboard so that it takes time to open. Then meanwhile we can discuss. Yeah, so sklearn.datasets, I'm importing this load digits, which is a real-time data set for the digit recognition problem. So I'm loading the digits. So you can see the digits.data.shape. This is of 1797 by 64. Means there are 1797 instances. Each instance is described on a 64 dimensional space. 64 because this is each instance is an image of 8 by 8. Okay, each instance is an image of 8 by 8. So each pixel we have taken as one feature. That is why 64 features. All right. So now So I'm calling this k-means clustering algorithm with a number of clusters equivalent to 10. Okay, and k-means dot fit underscore predict on the digits dot data. Digits dot data means only the feature vectors. Digits dot target means the corresponding target values. Okay, so we are not making use of target values while making clustering. So you got the clusters now. Now you can just see the shape of the centers. Centers are of shape 10 by 64 because there are 10 clusters. Each cluster size is 60. Each centroid size is 64. Right. So now, so I'm just plotting this
So
centroid.
one second, that 64.
64 is the
Earlier 64 was 8 by 8, 1 pixel.
here also 8 by 8 only, madam. You see, when you compute the centroid, the size of it is same as the size of the data point, right? Dimensions, number of dimensions in the centroid is equivalent to number of dimensions in the data point. Am I right? You're just computing the average of all this and all the data points in that cluster. That's what is the centroid, right?
Okay.
So each centroid dimension is 64 and there are 10 such centroids. That is why 10 by 64. Clear, madam?
Yes, sir.
Yeah. So now we're just plotting these centroids and showing them as the images after reshaping them to 8 by 8 images, right? So you see that centroids, you can see, tell me that what digit it is. First one, centroid of what?
Centroid belong to 4.
4. This one, 3.
3.
1, 2, 9,
9,
0,
0,
7,
7,
6,
5, 1.
5, 8. This is 8 actually, but it looks like it looks like 1. Yes, it is looks like 1. But this is 1, sir. This is 8. This results you will see in the result also that there will be a confusion between 8 and 1 that you will see. All right. So yeah, although it looks like 1 here, but it is a centroid of 8. Okay. So there is some confusion will be there between 8 and 1 also, that we will see. All right. So now what we do that after making the clusters, now we make use of this target values. All right. So now let me open a notebook. All right. So now after making the clusters, so let's say that this is one cluster. Let's say there are so many data points. Let's say there are 100 data points here and 80 of them belong to class 1 or digit 1. Some 15 of them belong to some digit 2 and 5 of them belong to some digit 8. So which label should I assign for this cluster? Majority voting, right?
1.
So
1.
1, right? It means I assign a label like 1 or digit 1 for all the data points belong to this cluster. It means I compute the mode of this points belong to each cluster and I assign a prediction label which is equivalent to the mode of that cluster. All right, that's what we do in this loop, right? So here you see that. So we are computing the mode of digits of target of mask and then we are taking that mask as this label, right? It means for all those data points, I'm assigning that all those data points belong to that cluster. I'm assigning that label. What label? Whatever is the mode of that cluster. Mode means, you know, na? More frequent one.
Yeah, most frequently.
Yes. So I'm assigning that label. All right. So now here I'm computing the accuracy score because we know the original labels digits.target and these are the predicted labels. I'm computing the accuracy score. I'm also computing the confusion matrix and printing the heat map, right? Confusion matrix, then taking the heat map, indicating that where are the more misclassifications with the different colors. So let me show you that. So this is the heat map. You see that all the diagonal elements are the correct classification. So 177 digit zeros are classified as digit 0. 55 digit ones are classified as digit 1. You see that all the diagonal entries are the misclassification. where you see the highest misclassification?
It has been misclassified as 2, 1, 1.
Yeah,
8.
between 1 and 8, right? Okay, so
Yes.
these ones are misclassified as 8 in 99 cases. This is the true label 1. The actual label 1 is misclassified as a 8 in 99 cases. This we also understood, right? When while seeing the centroids itself, we thought there will be some confusion between 8 and 1, isn't it? So that we have seen effectively in the results as well. Understood right now? All right.
Yes.
Similarly, there is a confusion between 5 and 9 also here, 42 cases. There is a confusion between 8 and 9 also, 48 cases. All right. These are the misclassifications. All right. Fine. So is it clear? There is a classification example using the clustering
Yes.
algorithm. Yes. So the next one is the image color compression, right? So first of all, color compression means representing the image with a limited number of colors. Representing the image with a limited number of colors. So like this. So can I represent the image with the limited number of colors? This is the original image. This is the image with the 16 colors. So can I represent the image with a limited number of colors without losing much information? Right. So for that purpose, here we are using the clustering algorithm. Particularly k-means I am using, but you can apply any algorithm. All right. So now how to solve this problem? You know how, so for this we have taken some data set, load sample image, in from which we are loading a particular image, china.jpg, and this is the image. It looks something like this. And this is the image of size 427 by 640, and there are 3 channels because it's a color image, right? The red channel, green channel, and blue channel. All right. So here we are normalizing the data to bring it to 0, 1 scale. All right. So this is the data dot shape. Okay. After reshaping it, so it means we are taking each pixel color as one data point because we want to cluster the colors only, right? When you want to compress this image, I mean color compress the image, we have to represent the image image with the limited number of colors. It means instead of taking so many colors, can I represent it with only 16 colors or only 20 colors? It means what? You are grouping the colors, similar colors, and representing all the similar colors with some common color. Hello, am I right? You're grouping the similar colors and representing all the similar colors with some common color or centroid color, we call it as. Hello, am I right? So, following or not? Should I repeat?
Repeat, sir.
Okay. You see that this is the image of 427 by 600. It means these many number of pixels. Okay. These many number of pixels. Okay. So each pixel is a 3-dimensional data because each pixel is a combination of red color, green color, and blue color. Am I right? So how many points are there? How many such points are there? 427 times
427 into 600.
600 or 624, 640, sorry, 640. So these many number of pixels are there. Now these pixels, we want to make them into 16 groups because we want to represent the image with only 16 colors. So it means each pixel is, we are making it into one of the 16 colors, right? So to represent it as the 16 colors, what we do is that we cluster all the similar colors into one group like this. And once we form a cluster of all the similar colors, we represent all these colors with some common color. So I compute the average of all these colors, whatever is that average color, I represent all these colors with the average color. Okay, so that way I will form 16 clusters and 16 average colors. It means 16 colors I can represent the whole image. Am I right? Hello?
Yes, yes, yes.
Yes. Got it right? It means
But
all these
initially there will be many cluster, but because we have to bring
many colors, not clusters. Many
okay,
colors.
colors.
many pixels are there. These many pixels are there. Each one of them is one color. There may be some
Yes.
repeated colors. Okay. You're making all these pixels into 16 groups, right? So that all the similar colors go into one group. Okay. So now after making this cluster, you are replacing all the individual colors with some common color, that is the centroid color or the average color. So now all these pixels belong to this cluster will be replaced with this common color. So like that there are 16 clusters. Therefore, you're replacing all the pixels with the 16 colors, right? So therefore, you are forming an image with only just 16 colors, representing the whole image with only 16 colors. Is that clear, ma'am?
Yes, sir.
Yes. All right. So now, yeah, you are reshaping this image into 2,73,280 by 3. So the actual size of the image is 427 times 640 times 3. You're reshaping it into 427 times 640 by 3. It means each pixel has one data point you are taking. Now you are applying the k-means clustering algorithm. We are applying the k-means clustering algorithm with a 16 clusters. 16 is the number of clusters. All right. So now new colors I'm taking as the cluster centers. All right. So and according to this new colors, I'm assigning the pixel values and reshaping that to the same size, chainer dot shape. So this is the recolored image. Now I am plotting this recolored image as well as the original image side by side using this imshow function. Now you see that this is wait a second. Oh, why is it taking a lot of time? Earlier it was not taking. Let's wait. But I have shown you already that, right? The first
Yes,
one
yes,
is
we
the
have seen the
original
image
image.
with the
The second
16
one is the 16 color image. You can try multiple values. You can play with it. You can try 20 colors. You can try 10 colors. You can try 5. You can try 2. All right, something like that. You can try and see that what is happening. You can play with it. This code is already shared with you, so you can play with it. All right. So that's all. I hope you have enjoyed this image color compression. I like this at least. Yeah, this is this 20 colors with 20 colors. All right, you can play with it. Okay. So I'm giving it to you now. If you have any queries, I can take. Otherwise, we can wind up the session. So thank you very much and happy learning.
Thank you, sir.